Hello everyone, in this video we're going to talk about how we can simplify some expressions that contain variables. So the properties of rational exponents and radicals can also be applied to problems that look like the ones we're going to look at in this video, or to expressions involving variables. So because a variable can be positive, negative, or zero, sometimes absolute value is needed when we are simplifying a variable expression. So what do we mean by that? Let's look at this table here. So n, that is our index, so that's like if I was doing square root, my n would be 2, cube root, n would be 3, right? So if n is odd, look what happens to our expression. So if I'm taking the nth root of x to the n, well, the nth root and the degree that my variable is being raised to, those are going to cancel each other out, right? That'd be like if I was taking the square root of x squared, it would just be x. So if I put some numbers in here, let's say I'm taking the fifth root of 7 to the fifth. Well, that's going to cancel out. It's going to just equal 7. And if I'm taking the fifth root of negative 7 to the fifth, it's going to be negative 7, right? So for when n is odd, I don't have to worry about absolute value there because I got either a positive answer or a negative answer. But when n is even, so if I'm taking the square root of x squared, then I actually need to apply absolute value to my answer here. And let's see why. If I'm taking the sixth root of 8 to the sixth, well, that's going to equal 8. If I'm taking the sixth root of negative 8 to the sixth, that's also going to equal a positive 8. And so we've seen this before when we're looking at, taking the square root and we say, okay, it's positive and negative as our answer. Kind of the same idea here, okay? So absolute value, the only time it's not needed is when all variables are assumed to be positive. And so we're going to look at a couple questions today where I'll say, hey, for these 3 questions, we're going to assume the variables are positive. And most of the time when you see those questions, whether it's on homework or quiz or a test, that sentence will be there, assume all variables are positive. And when you see that, you don't have to worry about absolute value. So we're going to look at 5 examples in this video, 4 here and then 1 down at the bottom. So for example number 1, we have the cube root of 27 d to the 12th. So I'm going to break this apart and I'm going to write this as the cube root of 27 times the cube root of d to the 12th. So now from here, we know the cube root of 27 would be 3. We're taking the cube root now, so n is odd, so we don't have to worry about absolute value here. So the cube root of d to the 12th. So what I want to do is I want to separate d to the 12th into multiples of 3. Why 3? Because if I do the cube root of d to the 3rd power, that's going to just give me the variable d. It's going to cancel out. So I'm going to write this as the cube root of d cubed times the cube root of d cubed times the cube root of d cubed and times the cube root of d cubed. So now we have 4 factors of cube root of d cubed because d cubed times 4, or 4 of those would be d to the 12th, okay? So now all 4 of these factors here are going to just give me the variable d because they're all going to cancel out because my index is the same as my power of my variable. So this is going to be 3 times d times d times d times d, which would just equal 3d to the 4th power, okay? All right, now number 2, we have the 4th root of x to the 4th divided by y to the 16th. So we do know here, we see that our n, our index is an even number, so we might have to apply absolute value here. So let's go ahead and break this apart and let's write this as the 4th root of x to the 4th divided by the 4th root of y to the 16th. Now, in the numerator, we get the 4th root of x to the 4th. Well, this looks exactly like that table that we looked at a minute ago. So we know this needs to actually be the absolute value of x for our numerator, okay? Now, for the denominator, we're kind of going to do the same thing we just did on example 1, but now I have the 4th root, and so I want to separate y to the 16th into multiples of 4, which is once again going to give me 4 of those. So we're going to have 4, or the 4th root of y to the 4th times the 4th root of y to the 4th times the 4th root of y to the 4th and times the 4th root of y to the 4th. So now, all along the denominator there, so my numerator is still the absolute value of x, but my denominator, all of those factors are going to just give me y. So y times y times y times y. And so my final answer would be absolute value of x divided by y to the 4th. Okay. All right, now for the last 3 examples, we are going to assume all variables to be positive, so we don't have to worry about absolute value. So for number 3, we have the cube root of 2a to the 13th, b cubed, and c to the 8th. So let's go ahead and break this apart just like we did on number 1. Let's write this as the cube root of 2 times the cube root of a to the 13th times the cube root of b cubed times the cube root of c to the 8th. So now as we go through, we're just going to kind of simplify as we can, and then we'll put our answer back together at the end. So the cube root of 2 we can't do anything with, so let's just leave that as the cube root of 2. All right, now the cube root of a to the 13th. What we need to think about here is how many multiples of 3 could we get from 13 so that we could factor out or simplify out some a's outside of my radical. Okay, well, we have 13, so we know that 12, at least 12 of those a's, we could put in groups of 3, or excuse me, in groups of 4, right? So we have a cubed, a cubed, a cubed, a cubed. That would be a to the 12th. And then we have one more factor of a. So once we do that, we're able to actually pull out an a to the 4th, okay? And then we still have cube root of a. So now, what did we do there? Well, in order for us to pull out a to the 4th, we had to have had 4 cube root of a cubed, okay, factors. And so once we do that, cube root of a cubed 4 times, that's the cube root of a to the 12th, right? And so we had 13, so we have one more a, and that's why it's still a cube root of a. Okay, now for b, the cube root of b cubed is just b. And now for c, we're going to think about the same thing. So how many factors of 3 can we pull out from 8? And that would be 2, right? So this would be c squared. And then how many c's will we have left? We still have 2 left, right? So what did we do there? We had like cube root of c cubed times cube root of c cubed times cube root of c squared, right? Because cubed plus squared, that's going to give me c to the 8th power, because what our exponent rules told us, remember, if I have the same bases and I'm multiplying, then I actually add my exponents. So now let's take a look at what terms we have outside the radical and what terms we have inside, and we're going to write it just like that. So we're going to take a look at the terms that are outside, so a to the 4th, b, and c squared, and we're going to write those first. So I'm going to say a to the 4th, b, c squared, and now I'm going to write cube root of, and I'm going to write everything else, 2a and c squared. So this would be my simplified version of what we started with on number 3. All right, number 4, we have x squared divided by the cube root of y to the 13th. So for this one, we're going to leave this as x squared for right now. But now on the denominator, let's think about how we could break this apart. Let's write this as the cube root of y cubed times the cube root of y cubed times the cube root of y cubed. One more cube root of y cubed. Now that gives me 12, right? Y to the 12th. Well, we had 13, so we have to do the cube root of y at the very end. So now we have x squared in our numerator. In our denominator, these 4 factors of cube root of y are just going to give me a y, right? So that's 4 factors of y, so that's y to the 4th. And then we do have a cube root of y in the denominator. Now, we can't leave a radical in the denominator, so we're going to have to multiply. We're going to have to rationalize this denominator. So we need to multiply by, the same thing, numerator over denominator, so it's like multiplying by 1. So a fraction that has the same numerator and denominator. But also our goal is to get this radical out of the denominator. So what can we multiply the cube root of y by in order for it to become just y? Well, that'd be the cube root of y squared. So we're going to multiply that on both numerator and denominator, because when I multiply the cube root of y times the cube root of y squared, that's going to become the cube root of y cubed, which cancels out to give us y. So now in the numerator we have x squared, cube root of y squared, divided by, and essentially we've just given ourselves another factor of y, so this is going to be y to the 5th now. Okay? All right, and so our last example that we're going to look at, down here we have 16xy to the 1/3 power divided by 8x to the 2/3, z to the -4th. So what I like to do whenever there's division is separate the division with my like terms. So 16 divided by 8, those are both constants. X divided by x to the 2/3, and then we have y to the 1/3. There's no y in the denominator, so I'm just going to write over 1, and then 1 over z to the -4th. because we didn't have any factors of z in the numerator. So now let's just simplify each of these fractions. 16 divided by 8 is 2. X would be like x to the first. And now this is a exponent rule where we have the same bases and we're dividing, so we can actually subtract those exponents. So 1 minus 2/3 would be 1/3, so x to the 1/3. Y to the 1/3, because we're not doing anything with that. And now we have a -4, or z to the -4th in our denominator, so to make that positive, right, we can't leave negative exponents. To make that positive, we can just flop it to the numerator. So that would be z to the 4th. So that would be our final answer there for number 5. And that is how we can simplify some variable expressions.